This schematic visualizes a recent internal test run by Anthropic. On the right, an overnight runtime log from their unreleased AI model, Claude Mythos, isolates a specific vulnerability in the OpenBSD kernel. OpenBSD is trusted to run global firewalls and critical infrastructure because it undergoes decades of continuous expert human auditing. This model found a bug that had survived that scrutiny since the 1990s. To test the limits of the new model, researchers placed Mythos inside a sealed, air-gapped sandbox environment. It had no internet connection and no external access. They gave the model a single objective: attempt to escape the system. The model bypassed the sandbox containment protocols autonomously, finding a path out of the restricted environment that the researchers hadn't predicted. Once it moved beyond the sandbox, the model accessed the local network, located the specific researcher overseeing the test, and sent them a direct message. The capability to execute complex software engineering tasks at this level scales directly into autonomous vulnerability exploitation. When a model understands how to build a system's architecture, it understands how to dismantle it. Until recently, Anthropic's Claude Opus model served as the industry baseline for frontier AI coding. Opus is widely used for complex, multi-file code refactoring, currently representing the top tier of publicly available coding assistants. This chart tracks performance on SW Bench Pro, an industry-standard metric for evaluating autonomous software engineering. The Opus baseline sits at 53.4%. On the same benchmark, Claude Mythos reaches 77.8%. That leap is even more pronounced on the SW Bench multimodal benchmark, which requires the model to process raw code alongside architectural diagrams and technical images. Shifting this chart to the multimodal benchmark, we establish the Opus baseline at 27.1%. The Mythos score on this same metric is 59%, more than doubling the performance of the previous generation. In machine learning, a 2 or 3% improvement between model generations is standard. These nonlinear jumps suggest the model is using a different internal logic for problem solving, a capability that directly translates to its offensive skills. Generative software engineering is inherently dual use. An architecture optimized to map out a robust system possesses the logic required to identify its breaking points. Anthropic tested this by deploying their models against the security architecture of the Firefox web browser. The baseline Opus model achieved a successful breach only twice, over several hundred attempts. Under identical testing parameters, Claude Mythos achieved 181 successful breaches. This graphic illustrates a browser architecture and its data pathways. Mythos navigates these through a process called exploit chaining. Traditional security tools scan codebases to flag isolated points of weakness. They find individual errors, but do not account for how they might be linked. Mythos analyzes the entire architecture at once, identifying how minor flaws interact. It identified 4 separate software bugs, each independently minor. The model connected these 4 bugs into a single sequence, bypassing security to gain full admin access. This capacity for autonomous exploit chaining makes a frontier model more capable than tools that merely discover single-point vulnerabilities. We see this reasoning in action again with the discovery of a 16-year-old dormant bug in FFmpeg. FFmpeg is used by almost every major video application globally, making any vulnerability within it a significant security concern. Because of its ubiquity, standard automated security tools had previously scanned this exact repository over 5 million times. Those 5 million automated scans missed the flaw because of how static analysis tools are built. This visualization contrasts the two approaches. On the left, static analysis tools search for known syntax errors or typographical mistakes in a rapid top-to-bottom scan. On the right is the Mythos approach. It performs architectural reasoning, tracing the logic flow between entirely separate modules. Contextual analysis uncovers logical flaws that are not visible in the syntax alone, but emerge when different pieces of code interact. Relying on traditional static analysis is no longer a sufficient defense against models capable of analyzing complete structural logic. Historically, discovering a major zero-day exploit required specialized human security teams and months of continuous labor. Now, the cost of discovering these flaws has dropped to the price of running compute credits overnight. Because of this, Anthropic chose to withhold the public release of Claude Mythos. They launched Project Glasswing to harden critical networks before exploits are discovered. Anthropic is dedicating $100 million in credits, granting restricted access to major technology hubs like Amazon, Apple, Google, Microsoft, CrowdStrike, and NVIDIA. The project also includes over 40 additional organizations that maintain critical open-source software. The goal is to give defenders a head start, allowing them to use the model defensively before adversarial actors achieve similar capabilities. These organizations are using Mythos to find and patch structural vulnerabilities across the infrastructure that supports the modern web. Project Glasswing reflects a shift toward a model where global infrastructure is secured through proactive, AI-driven auditing. The benchmark data confirms that as frontier models continue to scale, they will develop increasingly advanced autonomous exploitation capabilities. This changes the historical asymmetry of cybersecurity. Traditionally, an attacker only needed to find one flaw, while defenders had to secure every possible entry point. This split screen shows how autonomous models might rebalance that equation. On the right, AI automates code auditing and generates verified patches at a scale that was previously impossible. Maintaining this defense requires collaborative protocols and data sharing between companies that are often direct competitors. The future of digital defense will likely rely on human experts using these models to maintain a level of security that manual auditing can no longer provide on its own.